Okay, so welcome to the last talk of this semester. So we are very happy to have Michael Groechenig from University of Toronto to talk about inertia stacks, gerbes, and intersection cohomology.
It's amazing you remembered the title. I didn't. So yeah, thanks. So this is joined with Dimitri Wyss and Ziegler. So yeah, that's about inertia stacks, gerbes, and intersection cohomology. So essentially, I'm going to start by posing some sort of a wake question, to which I'm going to give a very partial answer and then talk about it for the rest of this talk. So let's start with some kind of general setting. Let's say that we're working with a smooth Gaussian stack. This be a smooth Gaussian stack. So in particular, I'm going to assume that Y is a smooth scheme. And G is a linear algebraic group. And I'm also going to assume that there's a good moduli space. I'm going to call X. Sort of the calligraphic letters will be reserved for stacks, and then the kind of the usual letters will be reserved for the spaces or the moduli space in particular. It's the same one. So in practice, X is usually going to be a GIT quotient, and curly X is going to be the stacky quotient. So usually X is a GIT quotient. Corresponding moduli stack or stacky quotient. All right, so that's the setting. And so then, despite of the variety we're taking the quotient of being smooth, we should expect the moduli space X to be singular. So note that X is usually singular. Even though the atlas Y is assumed to be smooth. And so in terms of GIT language, so in the GIT setting, it will be true that the singular locus but that's sort of a caveat I'm going to explain later, is going to be given by the points which are strictly semi-stable. So now what is the caveat about? So there could also be sort of Gaussian singularities. So essentially ignoring Gaussian singularities, finite Gaussian singularities. All before points. All right. And so now the goal or the question I want to ask is, how can we compute invariance of the singular space in terms of the group action? So compute. Then I'm going to focus on a very specific invariance, intersection cohomology. Intersection cohomology of X using the stack. Let us develop some sort of equivariant understanding. Obtain a equivariant understanding. Group action of G on Y. So why? Well, essentially, we already know that the singularities are situated in the locus where the stabilizer group is trapped. So why is this a good idea? Well, if it isn't, singularity is here as soon as stabilizer groups chop. So that's essentially basic observations. Now the question is, can we kind of understand this connection between the geometry of the action to the point that we can compute like an invariant of the singular space, namely intersection cohomology, in terms of the group action itself, the geometry of the action. And so as I said, I'm going to give a very partial answer to this, but still somehow it looks, so the answer which I'm going to give some sort of a formula for intersection cohomology, and the other side of the formula seems to be meaningful in more formal settings than where we can actually prove the comparison. And so now, so what's the settings for today? So we give an answer for X being a moduli stack associated to an abelian category. A satisfying some conditions. And so out of the conditions, the most important ones are the following. Most importantly, so finiteness. Maybe I should start with this one. I'm only going to consider categories which are linear of a finite field. Then we assume a finiteness of forms and higher x. We assume symmetry of the Euler form. By this I mean something for the next part. The Euler form is sort of a pairing. The group of A times itself to Z. Where you associate to a pair of objects, or isomorphism classes of objects, or K-theory classes. Essentially the rank which is some sort of Euler characteristics and applying it to K-theory classes. So let me maybe make this more explicit. Right, so something like that. So that's the Euler form. We want it to be symmetric. And then the last assumption is vanishing of higher x. So above x2, I don't want any non-trivial x. And so this is related to smoothness. Smoothness of the stack of objects.
Sorry, is there an x2 or not?
No. So just on Hom and x1 essentially. Okay, and so this is just related to smoothness of the moduli problem. And then given, so as a first approximation, given this, one can associate a moduli problem or a stack if you want. Actually, one needs a bit more data. So I'm going to come to this later. But then for stacks of this type, I'm going to give a precise way of how to compute the intersection homology of x in terms of essentially how to compute the intersection homology of the moduli space in terms of the stack. Okay, but yeah. Now let's take a look at a quick example first. So the symmetry assumption is maybe the one which is most unusual. I think linearity of a base field is quite common, and also finiteness of Homs indexed. I mean, if you take vector bundles, or if you take coherent sheaves, for instance, on a proper variety, it will satisfy these assumptions if the variety is defined over a finite field. Unless for symmetry of the other form possible. So that's the most curious one. Let me focus on an example, using an example that is symmetric. So here you can take any symmetric quiver. So this means every edge, there's an edge going in the reverse direction. But then you study representations of this quiver. So finite dimensional representations. So that would be an example of an abelian category, which is FQ linear, has finite Hom and X spaces, and a symmetric Euler form. And essentially, the Euler form can be expressed in terms of this directed graph data describing quiver, and the symmetry of the quiver just translates into symmetry of the Euler form. All right. So actually, this example will appear again later in this talk, and so maybe as preparation for that, let me tell you what the corresponding stack is and what the moduli space is. So in this case, the stack, if you want, in Q, for the simplest dimension vector, which is 1, 1, so you put representations with dimension vector 1, 1. So it's just one-dimensional vector spaces at the nodes, and then you have linear morphisms at the edges. And so as a stack, this will be equivalent to the quotient given by the affine space, quotiented by GM with respect to the hyperbolic action, if you want. Say this is the hyperbolic actions, or by this I mean you have weights plus and minus 1. Reducing these hyperbolas as orbits. And then the moduli space itself, the good moduli space, is then simply given by a copy of A1. And the map from the moduli stack to the moduli space is a sort of a product map. If you want to sort of associating to each orbit, I don't know what you say in the case of hyperbola. Do you say the radius? I mean, sort of each hyperbola is like given by solutions to the equation lambda times mu equals c. You're sort of associating c to it. I don't know what's the name of this. I don't know. But yeah, that's the map for the good moduli space. And in this case, and so this is actually a silly example for this talk, but still the one I'm going to discuss. The moduli space happens to be smooth, but in a way that's good because it makes it easy to compute intersection cohomology. So yeah, it's silly, but actually will still be not trivial. Okay. So now it's time for a short technical interlude for how to actually formally define these moduli stacks into ungiven abelian categories. Because in the example I just described, in a way, I didn't give you enough data to actually define stacks in the proper sense. So actually one needs to set things up, if one does things formally, one needs to set things up slightly differently. So actually what one requires is a very big category and a small category. So we actually need two categories. One is called B. So it's a co-complete FQ linear abelian category. And so somehow actually the important property is the fact that it's co-complete. Then in this, under these assumptions, Artin and Shang have shown that there exists a sort of an external tensor product construction. So you can take any module over the base ring, in our case would be FQ, and tensor it with any object in B, and get a new object in B. Sort of an external tensor product. So on the left you put a K module, and on the right you put an object in B, and you kind of there's a canonical way in which you can define such an operation that has satisfies certain properties. And it's pretty much like the usual tensoring operation for modules. So such that there is a notion of flatness and also descent theory. So now, given that, what one actually does is one starts with this co-complete FQ linear abelian category B. And then inside of the FP bar objects, one singles out a small category, A bar, which is assumed to satisfy the assumptions I just gave you. So this one satisfies finiteness and symmetry and the vanishing assumption. Okay. The whole point of B is actually just to provide the moduli framework, to give a formal definition of moduli stacks, of the moduli problem, if you want. Because in this setting, one can always define. Actually, there's one assumption here, so I want A bar to lie in the sub-objects of finitely presented objects in B. You can always define a moduli stack of finitely presented objects in B. Okay. Then this is sort of if you want, the mother moduli problem. It's then later restricted to families where the geometric points belong to A bar.
So it's possible to say what flatness means? Or is it possible to say one word on what flatness means?
Absolutely, yeah. So it's like if you take like an R family of objects in B, so it's essentially like you take an object in B with some R module structure.
It's a notion of BR.
Exactly,
Okay.
yeah.
Okay.
Yeah, and then you kind of want tensoring, right, with any R module to be exact, yeah, exact factor. Yeah. Right, so now we have this sort of this formal setting, and this allows us to define a stack. So we're not claiming any algebraicity or anything like that. We also don't need it, actually, when doing these things. But this allows us to define a stack. A stack, which I'm going to denote by MA. So this is sort of abusive notation, because I'm actually, in the formal setting, I'm only defining B over FQ and A bar over FQ bar. But yeah, nonetheless, I think the notation is more user-friendly this way. So this is essentially the stack of R families of finally presented objects in B with the K-bar fibers in its category B bar. Okay. So that's sort of the formal definition of this moduli problem. And then to make things a little more obscure, I'm going to define a second stack.
Sorry, families means flat families?
Yeah. Absolutely, thank you. Yeah, that's really important. Yeah. And so it's sort of the fact that this is an actual stack that you have gluing and so on is all kind of a result of Arithmetic in very high generality. So here I'm just working over base field, but actually you can work over arbitrary base rings and so on. Like that's what they do in their papers. So at least that part of the paper is kind of over arbitrary base rings. So now the next stack I'm going to need is the GM rigidification of MA. So just like defined by Abramovich, Olson, and Distoli. And so this is the first approximation. This means that MA, roughly speaking, has the same objects as the blackboard bold MA, but the automorphism groups differ. So you're just kind of dividing by GM. You're dividing away the trivial scalar automorphisms. Then you have to sheafify or stackify again to get a well-defined stack, but that's roughly speaking what one does. And so essentially the rest of this talk, I'm going to take a stack of this shape, MA, assume it's a global quotient stack, which it often is, in the example, at least in the examples we care about, and then give a way of kind of producing the intersection cohomology of the associated moduli space using the stack. So now in the rest of the talk, consider MA, assume it's a quotient stack, and try to find a formula. Of the intersection homology of the good moduli space. Which is usually singular. Okay. So that's what I'm trying to do. And any questions?
Do you really mean it is a good moduli space?
Well, it's a very good point. So you're absolutely true that you're absolutely right that in characteristic P, one actually has to maybe say adequate instead of good. There's a formal definition of what it means to be a good moduli space in the theory of stacks. And usually it's sort of, things derail a little over finite fields. So there's another formal definition, which is adequate moduli space. But actually, it's really like in examples, it's really just sort of a GIT quotient where you have some reductive group action and so on.
Is there some hope to use these formulas to say recover the intersection cohomology like toric varieties or some special class of toric varieties? Or the...
I think, yeah, there is hope. Yeah, possibly, yeah. So it's a very good question. Yeah. So let me just say one more thing on this sort of obscure formal setting, so that the choice of B really matters. So it's sort of, it has an actual impact. It's not just a formal construct. It really has an actual impact on the resulting moduli space. For example, to show that the choice of E matters. And I'm going to do this over a different base field because over the complex numbers, there's a very easy example one can write down using the Riemann-Hilbert correspondence. But yeah, over the finite fields, I wouldn't know what to take, but I'm sure there are examples. So essentially, what you can take here is you can take A to be the category of finite dimensional representations of the fundamental group of a curve, a Riemann surface. Actually, it could even be a smooth variety if you want. And then we can embed this into arbitrary representations. This would be a co-complete category containing this one. And another embedding that we could choose would be into D modules. And that's another co-complete category. And so the first embedding produces sort of a moduli stack, which I will call Betty. So it's sort of related to the character variety. And it's the quotient of an affine variety by GLN. So it's sort of inherently affine in nature. And the second example produces a moduli space that I will call a theorem space. And both of these, or a moduli stack, and both of these moduli stacks are complex analytically isomorphic, but not algebraically. So the sort of the algebraic structure that you get on the moduli stack and also the moduli spaces, they're very, very different depending on the chosen co-completion. The same is true for the moduli spaces. So there's a complex analytic isomorphism, but not an isomorphism on the level of varieties.
Sorry, does this method allow you to compute the intersection complex of both in both cases?
Well, this example, well, this is for the example is for K equals C, right? But yeah, I mean, if we can consider both cases also the finite fields, and yeah, then you can apply it. Actually, no, sorry, you cannot apply it. Actually, you don't have vanishing higher x. Like what you can do is you can puncture the curve and then you can apply it. But if it's like dx2 corresponds to h2, right? Sort of by Poincare duality, you see that it will usually not be vanishing. So you
like punching the curve, sorry.
Like if you remove a point, then you get vanishing of higher x. But if you don't remove the point, you have the smoothness condition is not satisfied. More or less that.
And sorry, do you still get something interesting if you consider these moduli stacks after you remove a point on the curve, or?
It's still something people do. Usually they also kind of fix like the monodromy at infinity to kind of get better moduli problems, but it's definitely still interesting. Definitely that's the sort of moduli problem you would like to understand.
Sorry, my last question. Do you get a different answer? Do you get a different answer in this case? For these two?
If I do it over finite
intersection, yeah.
Okay.
Sorry.
Yeah, I mean, you would definitely get different answers for the drum problem with the Betty. Yeah. The sort of the ranks would be the same, but I didn't expect this question. So the weights, the Frobenius actions will be completely different. Yeah. Actually, my two favorite examples, the one I already told you, the symmetric quiver, the simplest kind. Then the other example that I really like is in my vector bundles on a curve, which seem to be semi-stable. So if you take C to be a curve, then we can essentially look at semi-stable coherent sheaves of slope mu on C. So there will be automatically vector bundles if the slope is finite. And inside of the category of all quasi-coherent sheaves, sort of as our choice of B. And so that just consider MA here. You just get the usual moduli stack of semi-stable vector bundles, mapping to the classical moduli space. And I was planning to discuss this because it's actually somewhat surprising that symmetry is satisfied here. So exercise, if you're bored, prove that it's symmetric. Prove symmetry of the order. And it's sort of interesting because symmetry really only holds on the smaller category. So it's if you embed this category into coherent sheaves, you drop semi-stability and the assumption of the slope, you don't get anything symmetric. So it's actually, a little, yeah, I found it a little surprising that you get something symmetric here. Right. Now, in order to state the formula, I need to discuss weights and Gerbes, because those are the ingredients, and also inertia stacks. So let me talk about weights next. There's an abstract story here first. So if you take a vector space V, so here we're going to work over an algebraically closed field because they don't depend on any arithmetic definitions, the weights. And we assume that V is endowed with an action by mu R. So in other words, we're given a map from mu R to GL of V. Then we're going to discuss a way of associating to this data a rational number called the weight of the action. And it depends on the character decomposition. Essentially, formula is that the weight of V is equal to the dimension of V of chi times the weight of the character chi. Now I just have to define this. So this is a rational number between 0 and 1. Such that if you map it to Q mod Z, you get the class of the character chi. Can also canonically view as an element of Q mod Z, because by definition, this character group of mu R is given by essentially an endomorphism of the cyclic finite subgroup scheme mu r. We can canonically identify it if the integer is modulo r set. So that's how you define the weight of a character, and then you define the weight of the representation in this corresponding way. And so now in geometry, this sort of shows up whenever you have an action of a cyclic group on a space. And so one way to kind of formalize this is to say, given a map of stacks from B mu r to some stack x, we can pull back the tangent complex and obtain a complex of mu r modules. Then if you want the action, the weight of alpha is defined to be the weight of the resulting complex of mu r modules. It's defined as the alternating sum of the weights of the tangent complex. Okay. So in particular, given this, given this construction, we obtain a locally constant map or the weight map which is given by, it starts at the twisted inertial stack, which is defined to be the mapping stack from B mu r to x, and it lands in the rationals. So that's the weight map. This will be one of the ingredients to express the intersection cohomology of the moduli space. So now the other ingredient is given by Gerbes. So recall that MA was defined as this GM rigidification of another stack like the actual true moduli stack of objects, sort of leading to a new moduli stack by dividing out the trivial automorphisms. So in particular, this map from the actual moduli stack to the rigidification is a GM-cher. I'm going to call beta. This will be the other ingredient that one needs. So given a chirp on B mu r, we can extract another number from it, which will be eventually a root of unity or an element of the cyclic group. And this is done in the following way. So you just kind of use that the Brouwer group the classifying space, the classifying stack over the algebraic closure is actually trivial. So this is trivial because it classifies group extensions of mu r by GM. So if you want, you can just kind of identify this with H2 EK R using GM, and then so that's sort of the classical theorem that if you look at H2 of a classifying space of a group, this is classifying group extensions or central extensions, I should say, central extensions. But since mu r is cyclic, it's very easy to verify that if there's a central extension, it's actually commutative, just because the cyclicity of mu r implies directly that all the elements in the extension group commute with each other. So this means it's just a usual extension of in abelian groups of mu r by Gn, then kind of using dualizing, like you can quickly show that also this has to split. So you just get that this group here is trivial. So then if you kind of pass to the classifying stack over a finite field, you just need to understand in which way you can kind of twist the descent data. And that's just given by essentially following. So this implies that H2 of dk mu r in Gm will be something like H1 of the field with coefficients in of mu r Gm. Again, this is sort of just because splittings are taught on this group. So you directly end up with set model set in a canonical way. So again, sort of the point of view we have on this is that this gives a map from the inertia stack or the twisted inertia stack using a chirp as an any chirp on a stack M induces another function is given by that is invariant of the chirp. Given chirp vector is an element of the Brouwer of a stack X, we can associate to it a function from k points of the twisted inertia stack to Q mod set. Just by evaluating the pullback of the chirp. Very important, this function is not locally constant. So that's just a function on the k points, just a set theoretic function. Actually, usually it oscillates in an interesting way. All right.
Is a finite field or?
Yeah, exactly. K is now again assumed to be a finite field. Yeah.
So it's starting from where K is no longer equal to K bar.
So for the weights only depend on the geometric structure.
Okay. After that.
Geometry of the action, and then everything relating to the chirps kind of needs finiteness of the base field. Yeah. It's really, I mean, the finiteness of the base field is really crucial to sort of, yeah, as we'll see for the formula. Okay, and so now I can finally state the main result, which combines all of these ingredients. let me first state it globally. Then state a local analog of it. But yeah, so the global version of the theorem we have is that if you look at sort of the intersection cohomology point count, this means you take the alternating sum of the Frobenius traces on intersection cohomology of the moduli space. Then this is equal to minus the limit as some formal variable goes to infinity of the analytic continuation of the following infinite sum. But this will be we need another sum. And here I need this expression. Okay. So sort of that's the global way of kind of stating our formula. So essentially, this side here, if you want, allows you to recover the L function associated to intersection cohomology. And so from that, using purity, you can really read off the ranks of the intersection cohomology groups. So this allows you to recover the L function. Yeah, using Beidou and BBDG, knowing this left-hand side is really equivalent to knowing at least as abstract vector spaces, cohomology groups of the intersection cohomology. Then on the right-hand side, we have this sort of very strange expression where so essentially what's happening here, there's several claims hidden. So first of all, I'm claiming that if you just take this here as an abstract generating series, which only depends on stack information, I'm claiming that this has a natural analytic continuation. Actually, it will be a rational function. And that analytic continuation has a finite value at infinity. So the limit at infinity exists, is finite, and oh, there's a t missing.
Yeah.
Very good. Okay. So yeah, this is a rational function in t. And although the power series expansion given here, the Taylor expansion doesn't converge when t is bigger than 1. Usually, the analytic continuation is well defined, and the value at infinity is minus the quantity I need up to some q factor that I always forget about. So this is minus the dimension of MA. Okay, just kind of related to the definition of the weights that I showed you. So this is sort of the global version. There's a local version too, which I'm going to state quickly. That's my talk.
What is the sum running over? Sum over x comma alpha?
Yeah, and I'm UR, M comma alpha. So if you want, you can just say, okay, this is running over maps from beam UR to MA. That follows alpha. The kind of isomorphism classes of those, right? Then essentially, you're kind of taking a weighted sort of a character sum of that, where the weight is coming from the action. So the weights that I described to you earlier, they produce certain q powers. But bear in mind that a priori they could be fractional. Then you also need a sort of a character which is coming from the chirp. And that chirp is really actually a canonical object that you have on these moduli problems. It's also the abstraction chirp to the existence of a universal family in most cases. Okay.
Is your stack MA quasi-compact? Is your stack MA quasi-compact?
Yeah. So this is like, since I'm assuming like it's a quotient stack, this is sort of built in there. It doesn't necessarily have to be quasi-compact. Yeah, but actually, so the local version is sort of circumventing this. So the local version is essentially, so does my talk end at half past or at 35? What's the 35? Okay. It's pretty much the same thing. It's just that you kind of take the you apply Groechenig-Lefschetz. So you obtain the global version from the local version by applying Groechenig-Lefschetz. So here you take some q power times the trace of the Frobenius on the IC complex. Point X. This will be the IC complex of moduli space. Now that you can express in a similar way, n is minus the limit as t goes to infinity of the analytic continuation of a similar sum as before. It's the same expression, but let me just kind of explain what the assumption here is instead. So here we only kind of consider those points that lie above the point X in the moduli space. So mapping 2. So this makes sense because if this natural map going in one direction, if you get a map from B mu R to curly MA, this induces a map from B mu R to just a moduli space, and that will always factor through. Real point, of course, it's the no automorphisms in the moduli space. Okay, so this is the local version of the same statement. So you can really get information about the intersection cohomology, also the DSC sheaf. Technically, it's a complement. Now let me go back to the silly examples. I'm not going to tell you how this is proven. It's not maybe after the talk. Sort of it's a very roundabout way. So we actually use sort of results from Donaldson and Thomas theory. And that's why we have this restriction on just the moduli problems we can handle. Because the results we require from DT theory, they only apply in this framework. Okay, so we don't really use a known definition of intersection cohomology. We don't use a standard definition of intersection cohomology to prove this. We use sort of a property that stems from DT theory. But now let me convince you that this is true by revisiting the silly example. So this was the moduli space of quiver representations of this following very simple symmetric quiver. We looked at MA being essentially, no, M being MQ 1,1, so dimension vector 1. So this is given by A2 quotiented by this hyperbolic action. by GM. And the moduli space, and so that's why it's silly, is just given by A1. So it's not an interesting testing ground to really see IC sheaves and the full beauty, but nonetheless, the IC sheaf is well defined. It's the constant sheaf, so that makes it very convenient to check the example. And the computation is still slightly non-trivial, so sort of you go through the definitions, it sort of happens to be true. But then if you apply this to a different moduli problem, like vector bundles on a curve, you can actually you obtain seemingly new formulas for the Frobenius traces intersection homology then. All right, so let's see if I can do this. So just to give you a feeling for how this formula would be applied. So since we're looking at one-dimensional representations or one-dimensional representations, they have this shape. And in particular, if one of the two numbers is non-zero, then this representation will be always irreducible. So this is irreducible unless both lambda and mu happen to be zero. And so this is going to be crucial. And this matters because if you look at a point in I mu r, M, if this belongs to the non-trivial part of I mu r, where the I mu r action is somehow non-trivial on the object, this always gives you a splitting into characters, according to characters. So this means that the irreducible ones, they cannot lie in the non-trivial portion of mu r. So by this I mean I mu r of M minus the canonical embedding of M that you have via the identity map. So this always maps to the reducible ones. Reducible representations. And in this case, that's a single point corresponding to this representation. So that makes the computation a lot easier. And so then essentially, what do you end up with? But let's say we're kind of focusing at the origin of the moduli space. And then we get contributions from the representation 1, 0 and 0, 1. So maybe let me write it more clearly like this. And we also get contributions from, both of those are irreducible. We get contributions from the reducible one. Then sort of the actual series that you end up writing down will be something like that. So you get 2 Q inverse times TR minus plus Q minus 1 times Q minus 1 divided by Q minus 1 times TR. Then here you get this series here. And so those sort of match. So those are the kind of the contributions of the reducible one coming from the non-trivial elements of the inertia stack. So those are the contributions from the non-trivial part of the inertia stack in the point x equals to 0. That's just because any non-trivial mu r action will induce a character decomposition, and essentially the r-1 possibilities that you have, because you don't want this to be the trivial actions again. Yeah, that's where the -1 is coming from. And then here you get the 2 here corresponds to the fact that we have these 2 points, irreducible representations. And then here, that's this contribution here can again be associated to this reducible decomposition, but with the trivial action. Yeah. And then if you evaluate things at infinity, you end up with -Q inverse, which matches with the formula, because so the minus sign is just kind of the reason for why the minus sign appears in the theorem, sort of the value at infinity of the geometric series here, constant coefficients. And that's also what you get for intersection cohomology. If you do this for any other point, you get the same result, and you just see the Frobenius traces of a constant sheaf. Okay, I guess I should stop.
Other questions? And there are some applications.
I wish I could say yes. Well, in a way, I mean, this is like only half of our paper. I would say the paper is actually more about p-adic integration. So usually I give talks about that focus on the p-adic integration aspect, and to focus on the other half. So that's actually how we found the formula, and that's why we decided we had to prove it. So the actual application is, if you want, that for moduli spaces of this type, you can relate certain p-adic integrals to intersection cohomology. And then this allows you to prove, for instance, reprove chi-independence results on intersection cohomology using p-adic integration.
Which results, sorry?
Chi-independence results. So for this is again kind of DT theory, that's this conjecture by Toda that DT invariance for moduli of sheaves on surfaces should be independent of chi. So essentially the degree, some sort of degree independence.
Independent.
Yeah, independent. Yeah. And the geometry of these moduli spaces changes quite drastically. Like here, it's kind of comparable to changing the slope of vector bundles. Like if you look at vector bundles and you kind of change the slope, you pass from singulars to something very smooth. In this setting, you don't expect chi-independence. That's on a curve. But if you look at sort of Higgs bundles with various slopes, you actually do get chi-independence. You do get independence of degree for the certain cohomological invariance that kind of fits into this framework. Yeah, Toda predicted independence. You can see this using p-adic integration, and kind of, if you want to deal with the singular spaces, you need formulas like that, essentially. Yeah.
So, and then how does intersection cohomology features in the GD theory in this context?
It's just for those moduli problems, what they call the Donaldson-Tonner sheaf is essentially just IC sheaf. Yeah. So this is like in the homological dimension 1 case. Otherwise, it's way more complicated than that. Yeah.
Is there like a complex version of this where try to describe the mixed Hasse structures at the various points?
I believe this is work in progress by one of my collaborators, Wyss and Löser and Fauré. So they want to do like a motivic integration version of this formula. And then you can, at least get the Groechenig classes and mixed Hasse structures, get a comparison. But somehow this limit, I find it very mysterious, because like if you just look at the kind of the shape of this formula, it's sum of minus the limit as t goes to infinity of these terms. If you apply it to a Dirichlet-Mumford stack, you actually just get usual orbifold cohomology. So it's computing a known invariant there. So somehow I expect that this is sort of, that there is a bigger picture, that remains to be understood. Yeah.
So do you hope that you can have similar formulas for just like abstract quotients by By reductive groups or
What do you mean with similar formulas, like describing
the intersection cohomology?
without knowing that it's a moduli problem?
Yeah, yeah.
Like, yeah, then we don't know how to link it to intersection cohomology, because we really, like, what we show is that this limit, this value in infinity, it's actually, it can be written as a plethistic logarithm, and then that's also how you can describe the EIC sheaf, like the Donaldson Thomas sheaves essentially. And then, yeah. So we use results of Davison and Meinhardt from BT field to kind of connect it to intersection cohomology, but it's very indirect somehow.
But do you hope that this similar formula will just always work, or this is an expression?
I don't expect to always get intersection cohomology. Like maybe if you take moduli spaces of smooth quotient stacks, you can expect to get something like orbifold intersection cohomology. So that's because if you take a smooth Deligne-Mumford stack, that's what you get from this limit. So it will be sort of a mix. Yeah, I don't even know how to define it, but let me call it orbifold intersection cohomology. And otherwise, I don't know.
Does the moduli problem give you any control over the singularities of the good moduli space?
I think in a way this indicates that it does. Yeah, I mean, you definitely kind of in an ad hoc way, you kind of get sort of a local, when you work with these things locally, you kind of describe things in terms of, you know, general linear groups, and usually it's easy to rule out kind of the existence of finite stabilizer groups and stuff like that. So definitely gives you control over the nature of the singularities, but I find it difficult to actually formally say to what extent.
If you set this up on the complex side, are you getting like terminal singularities or any that type of control, or system of nature?
I'd be inclined to say yes, actually, because I know the p-adic integral is well defined. It's someone that indicates that the singularities can't be too bad. Yeah. Don't cite me though, but I'm inclined to say yes.
Any more questions? No, let's thank the speaker again.